This is demonstration number 5. What we're going to do is derive the parameters for an absorption measurement sequence that allows you to determine the equilibrium dissociation constant of a weak acid. So we begin with the basic acid dissociation equation or reaction. We recognize that there's an equilibrium constant defined as indicated, and that if we take the negative log of this equation, we determine that the pK is equal to the pH minus the log of the ratio of the dissociated to the undissociated acid. So if we happen to have unique absorption properties for the protonated and deprotonated form, we can use that information to determine the ratio concentration of the A minus over the HA. So just recalling that in the Beer-Lambert equation that the absorbances of multiple species in solution is additive. I'm going to factor the path length because that's not going to change in the course of this series of experiments, and ultimately I'm just going to drop it. So if I have a situation in which HA and A possess unique absorption properties, and again we're assuming there's a single wavelength involved, I have the following representation, which I would add to give the total absorbance for the measurement at a given pH. So what I want to do I don't know the epsilons, I don't know the molar absorptivities, but I can work around it by taking independent absorbance measurements of a system driven to high and low pH. So what I'm going to do is conduct two preliminary experiments. I'm going to drive the system basic by adding sodium hydroxide, and that will render all of the weak acid into its deprotonated form. I'll take another aliquot and I'll drive that to the protonated form by adding 10th molar HCl. So I'll have I'll have all the material driven one way or the other. I know that the analytic concentration here indicated by C subscript T is equal to the concentration of the protonated and the deprotonated forms. So now, if I have the absorbance measured within the sodium hydroxide solution, I have the only extinction coefficient that is relevant is that of the deprotonated form, and I can expand that as indicated. So I have the extinction coefficient of A multiplied by CHA plus extinction coefficient of A multiplied by concentration of A, in which case it would be 100%, but bear with me. If one does the same with the system driven in the HCl, I have the same situation. So I've got the following expanded equations. What I'm going to do now is subtract each of these two independently from the absorbance at an arbitrary pH. So recalling that at an arbitrary pH, a buffered solution, for example, I have the following Beer's law representation, namely contribution from each of the species. If I now subtract the absorbance of the NaOH and expand it, I get the equation indicated, and I can start canceling terms. Similarly, if I do the subtraction from using the HCl data, I get the following expanded equation, and I realize that I can first of all cancel terms and then group them according to concentration. If I do the algebra, I get the indicated equation, namely the absorbance at an arbitrary pH minus the absorbance in the NaOH solution is equal to a bracket expression, the difference between the two extinction coefficients multiplied by the concentration of HA. Similarly, if I take the difference between the absorbance pH and in the HCl solution, I get the differences in the extinction coefficients multiplied by the concentration of A. The bracketed terms are the negative of one another. And if I were to take the ratio of those, they would cancel, giving me a -1. However, if I reverse the order of the subtraction, namely in the second case or the first case, it doesn't really matter which one I do, I can get the signs to match. And in this slide, I've done that. I've reversed the order of the subtraction, namely absorbance of NaOH minus the absorbance at the pH. That gives me the reversal of the terms inside the brackets. They now cancel one another. In other words, become 1 as opposed to -1. And I have a ratio of absorbances, or the differences between absorbances, giving me the requisite ratio for the concentration of the deprotonated form and the protonated form. So now when I go back to the expression for the pK, namely the pK is equal to pH minus the log of the ratio of the concentrations, I substitute the ratio of the absorbances that I've measured, and the only parameter that's, well, really novel, this is relevant to the experiment, I would need the pH of the buffer, and I would need the absorbance of the buffer. The absorbance in the HCl solution and the absorbance of the NaOH solution have been determined previously. So with a single absorbance measurement at a given pH, plus the information from the driven systems I'm able to determine the pK for the weak acid.